So welcome back to the LTE interface training. We are now talking about the downlink reference signals. So we have 4 different kinds of reference signals. 3 are listed here. The most important one is the cell-specific reference signal. It's also called non-MBSFN. What is MBSFN? This is multicast broadcast single frequency network. This is a special operation mode which is not widely used. It's just for broadcasting. In this case of the broadcasting mode, we have specific reference signals which are designed for operation in single frequency network mode. And then we have UE-specific reference signals which are used for beamforming. And then in a later 3GPP release, we have something which is called channel state information reference signal, just to measure the signal quality. So now let's have a look at the cell-specific reference signals. They are evenly distributed on our resource lattice. As you can see here, this is a pair of resource blocks, and you see on one subcarrier the reference signal is repeated every half millisecond. So this time frame is defined by the expected Doppler shift we can have in the LTE system. LTE was specified to be used up to a speed of 500 kilometers per hour. And if we have carrier frequency of 2 gigahertz, then I get a frequency shift, or Doppler frequency shift of approximately 1 kilohertz. And this means if we take the sampling theorem, then we have to have a sample rate of 2 samples per millisecond. And this is the sample rate which is shown here, the repetition rate of the reference signal. Then we have a distribution in the frequency domain. The reference signal is repeated every 4 subcarriers. So we have a spacing of every 3 subcarriers with a spacing of 45 kilohertz. And these frequency gaps or frequency period is defined by the expected delay spread of the signal. So the delay spread is typically in the order of 1 microsecond, and this is equivalent to coherence bandwidth of about 20 kilohertz. And so we need a repetition of the reference signals every 45 kilohertz. And then we have the diamond structure, so they are shifted by 4 symbols if I go to the next subcarrier. So this is the distribution in case of normal cyclic prefix. In case of extended cyclic prefix, in one subframe there are 2 symbols less. So the overhead, of course, is higher of the reference signals, but it looks very similar, the pattern. Be aware of the overhead which is introduced into the system by the reference signals. But we need them for level measurement and for demodulation of all the user data which is included in the resource plane. So one important fact about the reference signal is the dependency on the physical cell ID. So if the physical cell ID is 0, for example, the first reference signal starts in the first subcarrier. So if we have a physical cell ID of 8, then the modulo 6 value of 8 is 2. This means our reference signal is shifted by 2 subcarriers. With this shift frequency offset, we can make sure that the reference signals of 2 neighboring sectors are not overlapping. So we saw the pattern for only a single antenna transmission. So we need, if we have several antenna ports, typically 2, then every physical antenna port has its own reference signal pattern. So the first antenna port is the antenna port 0, has the pattern which we have seen before. In between, we can put the reference signals of the second antenna port 1. And you see that if in the resource elements where the first antenna port transmits its reference signal, the second antenna port is muted. So, and vice versa. So with this muting, we reduce the interference between the 2 reference signal patterns, so they can easily be distinguished. So in case of 4 antenna ports, we have 4 different reference signals. So the first 2 we already know, and we have to add reference signals for antenna port 2 and for antenna port 3. Please mind that the repetition period of the reference signal of antenna port 2 and 3 is reduced. They are only emitted once per millisecond. So this means antenna ports 2 and 3 can only be used for lower speed. But this MIMO configuration is only significantly used for low mobility. So this is no real restriction. So one important function of the reference signal is the measurement of the level and the quality of the signal. And so reference signals can only be measured after synchronization, because only then we know on which symbols and on which subframes they are really transmitted. We have 2 types of measurement quantities. One is called the reference signal receive power, and the other one is the reference signal receive quality. The definition of the reference signal receive quality is n times the RSRP, the reference signal receive power, divided by the RSSI. This is the wideband receive power over all signals. So this means the RSSI includes all type of signals. This means the signals of the own cell, interfering signals from neighbor cells, interference from external sources, as well as noise. Everything is summed here. So this means the RSRQ is very much depending also on the cell load. If many resource blocks are transmitted, this will lower the RSRQ value. So it's dependent on the load. The RSRP value is the average of the received signal of the reference signal averaged over the whole bandwidth. And we have a mapping of an integer on the actual value, which is given in dBm. So the value range is from minus 44 dBm to minus 140 dBm, which is much below the detection threshold of most receivers, of LTE receivers. And 0 means reference signal received power less than minus 140, and RSRP value of 97 means receive level higher than minus 44 dBm. So the RSRQ is a measure for the quality of the signal, and we have seen the definition. RSRQ is n times RSRP divided by RSSI. N means the number of resource blocks. So we have seen before that we have two reference signals on one symbol in each resource block at least. So if we multiply by n, for example, if we have a bandwidth of 20 megahertz, then we have 100 resource blocks. This means 100 times RSRP. Then we have the transmitting power of half of the reference signals. And if the RSSI is only has distributions from the reference signal, then this means the RSSI is 200 RSRP. This means the maximum value we can get from the RSRQ is 1/2, and given in dBm is minus 3 dB. This is the lowest value we can get for the RSRQ. And you can see in the mapping table, RSRQ 0 means it's the lowest RSRQ value, which means the level is lower than minus 19.5 dBm. And dB, and RSRQ 34 means the RSRQ is higher than minus 3, which is the maximum. So let's come to some special reference signals which are not widely used, only for special operation modes. One is for the broadcast mode. You see the distribution of the reference signal on the resource blocks is very similar compared to the cell-specific ones, but they are offset by in time to not overlap with the cell-specific reference signals. And as well, you see they are repeated every subframe. And please remember that the repetition period in frequency is related to the coherence bandwidth, which is dependent on the delay spread of the system. And if we have single frequency networks, this means we receive the signal from several transmit towers. This means the delay spread is much higher than for normal LTE systems. And this is the reason why we have more reference signals on each subframe. And for the extended CP and the lower bandwidth of subcarriers of 7.5 kilohertz, we have a lower number of symbols, but similar pattern than for the normal configuration. Then let's have a look at the UE-specific reference signals. They are used in the case I make beamforming. Beamforming is individually directing the beam to specific users. And to make this happen, they need a special phase information, which is an offset to the normal cell-specific reference signals. So all the resource blocks which are dedicated or allocated to one user have additional reference signals which are added to the cell-specific reference signals. But they are distributed in a similar way to the cell-specific reference signals, but they are offset not to overlap with the cell-specific reference signals. You see the configuration for normal CP and for extended CP. And not shown here, but also now defined, are the CSI reference signals. These are channel state informations. They are very seldomly sent and only used for measuring the level or the channel quality. Thank you for watching.